QSO Today episode 259, Phil Erickson W1PJE. This episode of QSO Today is sponsored by ICOM America, makers of the finest HF, VHF, and UHF transceivers for the radio amateur that are ready to enhance your contest season. And by QRP Labs, Hans Summer G0 UPL's QRP Radio Kit Company. Hans has an amazing catalog of radio kits and parts for every budget. I want to thank both ICOM and QRP Labs for sponsoring the QSO Today podcast. Welcome to the QSO Today podcast. I'm Eric Guth, 4Z1UG, your host. Phil Erickson W1PJE sits on a 1,000,000-watt UHF transmitter at the MIT Haystack Observatory, where he studies the atmosphere and radio propagation. Phil is a longtime radio guy, but a newcomer to amateur radio. As you will hear in this QSO Today, the tools, modes, and technology of amateur radio are complementing the research achievements of scientists like Phil W1PJE. W1PJE, this is Eric, 4Z1UG. Are you there, Phil?
Yes, I am, Eric, 4Z1UG, your 5 and 9 plus 40 on this line. Good evening to you. It's afternoon here, and hello.
Yeah, thanks, Phil. Thanks for joining me on the QSO Today podcast. Can we start at the beginning of your ham radio story? When and how did it start for you?
Certainly. There's a couple of different things that happened to get me interested in radio, and in fact, that's laid down the foundation for my whole career. On my mother's side of the family, they came from Dutchess County in New York, a little town called Millerton. Specifically, we would go down to visit my grandmother and my uncle, who still runs a little, sundries and sporting goods store there, which is celebrating 100 years this July. So our family's been doing this for a while. And upstairs on the third floor, when I would visit, there was a Hallicrafters SX110 that my uncle had gotten in trade for something or another. Being a vacuum tube or a valve set, when you turned it on, it glowed nicely, and in the wintertime, it certainly kept the room warm. And being a person who was 11 or 12 at the time, I disobeyed my grandmother's instructions and climbed out in the hip roof and installed a long wire antenna. And when I would visit them, especially on a hot summer evening, just tuning around in the bands and listening to commercial broadcasters was sort of couldn't beat the attraction, especially tuning into things like Vatican Radio, which would only spend 15 minutes a day speaking in English, reading the news, hearing the little audio jingles like Radio Australia would play Waltzing Matilda for 5 minutes on the frequency to let you know they were there. And even more interesting, I got a bit of an illicit feeling tuning around and discovering the Voice of America. Even though as a U.S. citizen, I wasn't allowed to get a schedule. Turns out I found out much later there's something called the Smith-Mundt Act, which said that as a U.S. citizen, listening to the Voice of America would be propaganda. So I was tuning across this thing, but yet as a citizen, I wasn't supposed to be listening to it. So that was interesting to me. So from there, it gradually went down to a 1941 Zenith 10S567 console that was down in my family's store, which I'm pretty sure heard the declaration that FDR made on December 7th, 1941. This huge thing with an 18-inch speaker that you turned it on, and that very warm sound came out of it. So I got some time repairing that. When I wasn't visiting them, I was back home in Schenectady, New York, where I grew up. Our street had a lot of technically capable people on it. My parents both worked for General Electric's Research and Development Laboratory, and so radio became a part of my bedroom and the thing I listened to. In fact, we even detoured a family car trip to Canada at one point to visit the CBC transmit facilities in Sackville, which I suppose was a little bit unusual for the typical family trip. That was because I had heard, yeah, and that was also because I had tuned across the CBC North service, which would click into Inuktitut and Cree at some point, and those languages are so amazing to listen to that once again I got the feeling that the world was opening up to me just by tuning around. One other thing that kind of cemented my interest in radio and all things radio is, at the time, a fellow named Glenn Hauser, who is still around and now does the World of Radio, I believe, broadcast. He had a journal called the Review of International Broadcasting. It was this little thing that came in a 5 by 8 inch kind of typed up magazine. And my parents got me a subscription for that because this was before the wide availability of the Internet. This was the way you figured out where stations were going to be. And actually, Glenn called our house. I remember this at one point, sometime before the holidays, because my parents apparently were getting me this subscription. I picked up the phone and said, hello. There was this pause in the line and said, I'd like to speak to your parents. Being a good person, I said, can I ask who's calling? And there was this panic for a moment at the other end, and he said, Santa Claus. So the phone was handed to my father, and they commenced the negotiations. But listening to shortwaves was something that I did all through school. I never really got to transmitting until later, mainly because there weren't necessarily a lot of hams right near me down the street, for example. And then very quickly, as I got interested in physics and engineering and went into university, some of that took over sort of the impetus for technical work in constructing transmitters. And as we'll talk about a little bit later, I've ended up in a place with very loud transmitters. So in some sense, I have been transmitting. It's just been in a little different way than the typical ham would have gotten interested, I guess.
When did you get your first license, and what was your first call sign?
Believe it or not, not until rather recently. I think I was licensed in 2015 because I figured it was finally time. Okay, let's just go ahead and do this. But like I said, I had been hanging around with amateurs for many, many years, and the whole thing was triggered by my friend Skip Youngberg, who's a fellow in the Neshoba Valley Amateur Radio Club that I belong to. That's Kilo 1 November Kilo Romeo. He invited me to give a talk over at the club, which is the neighbor to where I'm speaking to you from at Haystack, in 2013. That's kind of what started it all. So Skip was one of my first Elmers. Another Elmer that kind of appeared on the scene is my colleague, Dr. Ethan Miller. That's Kilo 8 Golf Uniform. Ethan is at Johns Hopkins Applied Physics Laboratory. He's a colleague, a friend, and a very long-time operator. And then, like anything, when you start looking for amateur radio operators, you find them everywhere, especially in technical fields. So it turned out that one of the people is my colleague here, Will Rogers, Kilowatt Delta 4, FOV. Will has been an HF operator for many years. And then suddenly a fellow named Bruce Blaine, Kilowatt 1 BG, who was a very crack CW operator, came over, helped me string an antenna, and got me into doing some public outreach, in fact, involving amateur radio. So I've been very blessed to have these people show up and kind of get me started. After that, through some activities that we'll talk about a little bit later, I've been connected to people like Ward Silver, and whom I know you've had on the program, and Carl Welcher-Schwab, K9LA.
Who I've also had.
And my colleague Bill. Yes, indeed.
Indeed.
You've made the rounds.
Well, a long time ago, I think almost 5 years now.
Yeah, well, Carl's an extraordinary ham too, in that not only does he have all this extremely deep propagation knowledge, but he also keeps up with the scientific literature quite well. Usually, he's found out about something even before I have. So, Carl is a wonderful collaborator. And my colleague Bill Lyles, NQ6Z, is also involved. So I've been really, really blessed to have a number of people who have not only shown me the ropes just in my personal ability to become a full-fledged ham here, but also in just the curiosity that I hope we'll be able to cover a little bit later.
Oh, sure. So was your first call sign W1PJE? In
fact, it was. And because that way my memory could remember who I was. That's a vanity call.
Did you go from zero to extra in one sitting?
I did, and I probably should have warned the examiner that I was going to do that, because by the time I asked for the second piece of paper, he was getting a little bit concerned. And then when I asked for the extra set of questions, he was really confused. So I should have warned him. But yes, I did. Because, again, and by the way, I am also trying to rectify the lack of, requirement for a CW test by trying to get myself up to speed on that, trying to stick to head copy. So that's...
Oh, good for you. And what's the method you're using for that?
To tell you the truth, after learning sort of the basic letters, really with a couple of MP3 files that I found on the web, I can't remember the fellow's call who did that. Really, the best thing for me has actually been just tuning around and listening to traffic. That's especially contests. Contests tend to be easier because the exchange is predefined and your brain starts to pick up patterns. And I know that you interviewed someone who was talking about this Wordsworth method of not listening to just letters, but that's entirely the way to go for me, certainly.
Whole word.
Absolutely. And that's the way my brain works, and that's the way I learned language. So if anybody's thinking about embarking on a similar journey, I really do recommend that method. It's a little tough going at first, but then it's a nonlinear process. Suddenly your brain wakes up and starts. It's like when you buy a white car. After a little while, suddenly you see that everybody on the highway has white cars.
That's exactly right. Yes. Or you see a kind of car.
Yep, absolutely. Right. And so that's what I've been doing. I was going to say, I should mention that, if you think about first things that I worked with, in addition to this Hallecrafter's SX110 that I mentioned, I eventually ended up with a national NC125, which my father had found from someone for not very much money. This is a 1950s receiver. It's not the best radio, but it was something that I could work with. And I had one of those electrical engineering sort of early experiences. It turns out that on the back of that is an octal plug. And because it was intended for as accessory chassis, I think it was an FM chassis before they moved the FM frequencies up to 100 megahertz. The plug had 150 volts DC and the full B plus supply on the back of it. And at one point, I actually came into contact with the B plus very briefly. That was enough to curl my hair. So early on, I recognized the importance of keeping one hand behind your back. So that was another thing that I got to work with.
I saw the picture of that in your QRZ page, and it led me, I wrote a question down here that I was just wondering whether you've acquired and restored other vintage gear.
A little bit. Mostly it's been trying to keep the NC125 at least on the planet, and then every so often going back to this Zenith 10S 567, which is another beast in and of itself. It's one of those things that originally had the unpolarized plug, so if you flip the plug around, the entire chassis was hot. You have to be a little bit careful.
So you still have the Zenith 10S 567?
It, in fact, is operating as we speak in my uncle's store in Millerton, New York.
Oh, amazing.
There's a little bit of a family story that goes with that, too, is that we have a serious number of Anglophiles in our house, and in fact, in my family, including my uncle. And one of the things he really liked to do was to turn that on and tune into the Queen's Message, which comes out at 1500 GMT on Christmas Day. This is something that the Queen has done ever since her father, George VI, started in the 1930s. Message to the Commonwealth. So we kept the radio running, and unfortunately, the BBC has stopped their shortwave service to North America about 10 or more years ago because they figured that everyone was getting this through satellite feeds now. But there are many holidays where at 10 a.m. on Christmas morning, I had to interrupt the festivities to go down and get a tape recorder and record the message so that I could bring it down when I visited him later so we could find out exactly what she had said. So there's a connection there.
Did your interest in radio, in shortwave radio listening, did it play a part in the choices that you made for your education and career?
Absolutely. For undergraduate, I ended up at Cornell University, which is a very large university with a lot of different subjects. And I ended up in the engineering school, and I was a bit of a generalist, and I said, boy, there's all these interesting things, chemical engineering and mechanical engineering and civil engineering. How am I going to decide about all this stuff? And I looked over, and I said, oh, electrical engineering. Okay, play with radio parts. That sounds pretty cool. So I ended up going through and getting my bachelor's in EE, and then stayed on because that same department in graduate school was doing radar work, but instead of radars pointing at objects like airplanes, these were radars that they pointed upwards at the upper atmosphere and tried to scatter off the electrons and ions that are up there. And it's a natural outgrowth of being a double E. You know how to put signal processing together. You know how to put RF together. So it kind of one thing led to another. I decided I wanted to do research, so I ended up with a PhD from a space physics group, but my background was in electrical engineering, and that led to me becoming a researcher here at MIT Haystack Observatory, which is in Westford, Massachusetts, a little northwest of Boston. So I can trace that whole path back to sitting there on a hot evening on that third floor and listening to Deutsche Welle or VOA or something else coming and going. I really see a direct line.
What is the MIT Haystack Observatory?
Okay, so MIT is Massachusetts Institute of Technology, just to spell out all my acronyms. MIT, of course, is located in Cambridge, Massachusetts, which is much closer into Boston. Post-war, the famous MIT Radiation Laboratory, which was instrumental in doing radar development in the 1930s and 1940s, wanted to continue that kind of radar development. But they didn't want to do large antennas and powerful transmitters in the city of Cambridge because it was already, of course, quite crowded with people. And so they ended up buying a plot of land out here. It's about 50 kilometers or 35 miles northwest of Boston, which at the time was a sleepy area. This is where people from Boston had their three-season summer homes. And they bought about 1,300 acres of land, or about 3.5 square miles. Sorry for the English units. I should translate it into hectares at some point. And we're on top of a little hill, and this was so in the mid-1950s, Haystack Observatory here was really started as a radar development site. The timing was very fortuitous because just as the site was being constructed and getting underway, there was some developments for the ballistic missile early warning system, the thing that looks over the poles in the Cold War era. But you needed a fairly loud transmitter and a fairly large antenna. As all this was just finishing its construction, Sputnik 1 was launched on October 4th, 1957. And so it turned out that the site here ranged Sputnik 1 about 2 days after it was launched. So we kind of provided an early indication that the satellite was at the altitude that it was at. As you know, ham radio operators around the world were listening to its particular beeping, but this was an actual ping that could tell them that, yes, the orbit was about what the Soviets had claimed. And so we kind of got on the map rather quickly. Radar development kind of started. This was at UHF frequencies, 440 megahertz approximately. So, in the neighborhood of the 70 cent. Exactly, in the neighborhood. Mm-hmm. And then gradually, quickly, that went up to L-band, 1290, 1295 megahertz. Again, not that far from an amateur band. And then it went up to S and X-band. That's 2.4, 2-point-something gigahertz, depending. X-band is 10 gigahertz, and then we've gone beyond that now. In fact, one of the sensors here that is operated by MIT Lincoln Laboratory, which is a piece of MIT that does DoD work, that sensor is up at W-band. That's 95 gigahertz as a radar. So with a large antenna at 95 gigahertz, you can do interesting things. So gradually, this site as an observatory developed as a place to do advanced radio and radar development. And about midway through its history, maybe midway between the 50s and now, somewhere in the early 1970s, a program was created to do basic fundamental physical research, not just applied research for things like, Department of Defense. And so the program that I work with, and in fact Haystack is now administered by a department on MIT campus. So we do work for the Vice President for Research. We do basic research funded by writing grants to places like National Science Foundation, NASA, Air Force Office of Scientific Research. So there are radio astronomers here at Haystack who, don't make any waves, but they listen to waves being emitted by celestial objects. There are people like me who run a program where we'd like to figure out what's going on in the charged part of the upper atmosphere, but the charged part of the upper atmosphere doesn't necessarily transmit radio waves, so we have to make our own. So we use this UHF system left over from that original development back in the 50s, and in fact point it straight up and get a very, very faint echo from the ions and electrons that make up the upper atmosphere, the same ones that create HF propagation that, every amateur radio operator deals with from getting their signal from point A to point B. But we do this and then use that as a fundamental research tool. So that's some of the things that we do at Haystack. You can think of it as a multi-program place where we use radio waves for remote sensing in some form or another.
And now this message from ICOM America. Heard it, worked it, logged it. Now that field day has passed, we enter the contest season and hopefully more time to get on the air. It's time to get the ICOM transceiver that's best suited for your lifestyle. ICOM offers a variety of high-performance and innovative products. Make the most of the summer and contest season with one of these great ICOM rigs. The IC7610 is the SDR every ham wants, and just in time for contest season. This high-performance SDR has the ability to pick out the faintest of signals even in the presence of stronger adjacent signals. The new ICOM IC7610 is a direct sampling software-defined radio, SDR, that will change the world's definition of an SDR transceiver. The ICOM 7610 features include RF direct sampling system, 110 dB RMDR, independent dual receivers, and dual digicell. The IC7300 has changed the way an entry-level HF transceiver is designed. The rig is a high-performance, innovative HF transceiver with a compact design that will far exceed your expectations. I purchased one myself last fall and can tell you that the ICOM 7300 is as good or better than any rig I've ever had. The ICOM IC7300 includes RF direct sampling, 15 discrete bandpass filters, a large 4.3-inch color touchscreen, real-time spectrum scope, internal antenna tuner, and an SD card memory slot. No matter which ICOM rig you choose, you'll be a winner. Be sure to check out these fine rigs at www.icomamerica.com or click on the banner on the QSO Today show notes page. And when you finally go to make your ICOM purchase, be sure to tell the dealer that you heard about it here on QSO Today. My thanks to ICOM America for sponsoring the QSO Today podcast. And now back to our QSO. Now, does Haystack collaborate with HARP, which is the High-Frequency Active Auroral Research Program in Alaska?
HARP is part of sort of the general. We don't directly collaborate with HARP here, but we certainly have colleagues that work with HARP more directly. So one thing to understand is that it's also interesting to think about. Well, I actually, for the power levels that I need in order to get this very, very faint echo from the ionosphere and then interpret it to obtain, I'm kind of doing weather in the upper atmosphere. I'm looking for density and temperature and velocity and what the stuff is made of. But, I do need about a megawatt class transmitter and a 150-foot or 46-meter diameter antenna. And even with those things, the signal that I get back is a few femtowatts. It's, the signal-to-noise ratio is about 3 to 5 above the thermal noise floor, like when just what the universe is putting on us. You might think, wow, when you turn that on, that's a lot of power with a lot of gain. Don't you do something to the atmosphere? So I did this calculation for a bunch of students once, and even with that power level, it turns out that at the UHF frequencies I'm using, the sun every day when it wakes up puts about 100 million times more energy into the upper atmosphere than my paltry little efforts can. So at the frequencies I use, nothing much happens to the ionosphere. Now, if you go down to HF frequencies, which HARP does, you can resonate with the upper atmosphere. There's a different set of physics there, and you can raise the temperature a little bit. So people that work with HAARP actually use that as an active experiment. We raise the temperature a couple hundred degrees Kelvin, and then you turn off the transmitter for a little bit and watch it relax. And when you're doing that, you're actually doing an active chemistry experiment where you're figuring out things like thermal conduction, things like how fast do the ions crash into the neutrals. These are things you cannot measure in a laboratory. The upper atmosphere is a very different place. It is a place with very low pressure and very high temperature, and you just can't make it in a laboratory vessel. So HAARP does sort of active experiments to perturb the ionosphere in very small ways and see what happens. We are just doing diagnostics. So we are just measuring the normal thermal state of what's going on here. But to do it, we need something that's really large.
Now, you mentioned that the array that you're using was left over from the radar work. Is the 1 megawatt radar transmitter, which is talked about on the on the Haystack Observatory website, is that a transmitter also World War II vintage?
It turns out that I used the same transmitter that tracked Sputnik 1 in 1957. High power is high power. I'm not using the same transmitting tube. We use something called a Klystron, which may be familiar to some of your listeners. That's basically a tuned microwave cavity amplifier. It's got 4 cavities tuned to 440 megahertz. This was used in high-power radar work for these larger arrays that would put many of them together and, again, look for objects coming over the horizon and coming out of the atmosphere. So the cabinet I use is, in fact, the very same one. We've gone through a number of Klystrons since then. A Klystron, you start with an electron beam at the bottom. The electron beam comes out of the filament. And, again, anybody who's worked with a vacuum tube will recognize the filament boiling off electrons. It goes through this tube with a bunch of electromagnetics to pinch the beam, and then as it passes each one of these 4 cavities, the electrons stop becoming completely laminar or smooth, and they become bunched. And they bunch at the frequency that we'd like to transmit at. And at one point, we inject the signal that we'd like to. We sort of modulate it. And then eventually the beam comes out, appears at the top after 4 cavities. There's an output coupler, which then pulls off this now megawatt class wave. We've pulled energy out of the power supply, essentially, and used it to amplify this wave. The rest of the electrons crash into a collector plate. Again, looks like a plate. And then go back through the power supply and complete the picture. So it's a very clever technology that goes back to the Varian brothers and also Charlie Litton. And, in fact, if you go back in the history of amateur radio, you will find those names, in the 30s and the 40s. Once again, like many things, if you look hard enough, you find amateur radio operators innovating all over the place, and they were certainly people who did that out on the West Coast.
Now, I was looking through the MIT Haystack Observatory website, and there was a page for undergraduate students, and it said that undergraduate students are encouraged to buy and build an SRT, or a small radio telescope. I looked at the bill of materials. It looked like, you could put together one of these things for about $8,000. Would it be useful for amateur radio operators?
So the small radio telescope was developed by my brilliant colleague, Alan Rogers, who's a very distinguished radio astronomer. But he actually had a background. He grew up in South Africa and wanted to make sure that there were affordable instruments to be able to do radio astronomy rather than the $1 million class telescopes that you might expect from looking at normal facilities. So the SRT started life then, and it's essentially it's a combination of an older sort of 3-meter or 2-point-something meter class antenna that people used to use for satellite TV reception.
Right, C-band satellite TV.
Yeah, that's right. That's right. And it's primarily tuned to frequencies, the feed that is used is primarily tuned down in the L-band region because he's looking for the actual, turns out neutral hydrogen in the universe emits a faint signal when the hydrogen transitions from one state to another one. and that signal is about 1.4 gigahertz-ish. And so the idea is that with this particular system, it's sensitive enough to actually measure the rotation curve of the neutral hydrogen in our galaxy, measured over a long time, which is one of the fundamental things that you do for radio astronomy. So the SRT was developed to do that sort of thing. And there's a couple of hundred of them, maybe more than that, installed in various universities. You've already found the bill of materials, so you can see what that system is. He then later developed something called the VSRT, which is the very small radio telescope, which in fact uses direct TV dishes because you can buy them on eBay for nothing. And not only you get those, you can also buy a very nice low-noise quad-band, low-noise block feed, because there's these triple block feeds that you will see on a typical DirecTV dish. So he's converted the VSRT to do some other measurements. I would say from an amateur radio point of view, the design is fairly malleable, and shifting that down to frequencies that someone might be interested in, say at L-band or some of the higher frequencies with the VSRT, is not out of the question. It would be an interesting exercise for someone to try to do that. Certainly they can contact me, and I will forward that information to our team here. We're always looking for new people to sort of innovate on the SRT and the VSRT. They're interesting tools. The explosion in affordable samplers is, of course, no surprise to your listeners. It still continuously astonishes me what you can get now for almost no money. In fact, the RTL dongles, the kinds of things that I know are some people's first foray into software-defined radio, one of Alan's systems here is actually using that as its sampling. So it's very possible to do very good science with something that on the face of it looks like, geez, this thing is so cheap. How can this really do work? I would say, Eric, that is one message that I really should leave listeners with in general when they're listening to this, is that that explosion in technology of making things affordable at both the hardware and the software level, at a level that was unimagined even 5 years ago, has presented an interesting set of opportunities for people in that making measurements that are not professionally calibrated, but making a lot of them through things like machine learning, AI techniques, and other things, you can often extract science if you have enough measurements on devices that are not very well calibrated. They are not taken into a laboratory and shown a calibrated power source and precisely measured. That is one thing that we in the professional community are trying to work with as a new data source, as something that has a lot of science in it, but is not the traditional way that we would field, for example, a professional series of instruments. And when we talk a little bit later about this thing called HAMSci that I've been quite involved in, I think that's something to bear in mind.
Is there a relationship, or do you think that, because of what you've just said in terms of the availability of technology, I might even say that our ability to maybe even crowdsource around the world through internet connections, receivers and transmitters and things like this, is there a relationship between ham radio operators and space physicists now that could create a relationship that would benefit both physicists and ham radio operators? And how would you define that?
I would say the answer to the first question is absolutely, and that's why we've started this collective. My colleague Nathaniel Frizzell, Whiskey 2 November Alpha Foxtrot, who is a researcher at the New Jersey Institute of Technology, soon on his way to the University of Scranton in Pennsylvania. Nathaniel has been quite visionary 3 or 4 years ago in realizing that we needed to address precisely the question that you asked as your last question. How can we make science out of these measurements? How can we make amateurs and professionals meet in the middle? So the HAMSci Collective was sort of started as a way to get that dialogue going. And what we have realized over the last 2 or 3 years is there's a couple of keys to making the crowdsourcing of enthusiast kind of measurements yield real science. The first one is to figure out how to motivate the scientific method and the rigors that you have to go through to a technically literate population who is primarily trying to enjoy this as a hobby. You know, if I told you, well, I'd love for you to make this scientific measurement, but I'm going to need to tie up your IC 7300 for 1 year continuously, and you can't touch it, but we'll make these really great measurements. Well, you know, that's not as motivating as basically saying, if you get on the radio and you make some FT8 digital contacts and you make sure that they're uploaded to PSK Reporter, we can use that information. And furthermore, if we talk back and forth, we can show you how we're using that information, which will motivate more people to get involved, because we quickly realized that just doing things in a vacuum and seeing no response to it is not that motivating. So what we're doing in this HamSci collective, and this is some of the things I've been involved with, is trying to come in from the professional side and say, how do we use this data? And from the amateur side, coming in and saying, okay, we're really enthusiastic, we want to contribute to science, how should we contribute? So we're trying to meet in the middle, and we've had some good initial successes, but it's definitely a developing collaborative.
Let me take a quick break here to tell you about my favorite amateur radio audio podcast, the Ham Radio Workbench podcast with George, KG6VU, and Jeremy, KF7IJZ, where they pursue topics, technology, and projects on their ham radio workbenches every 2 weeks. George and Jeremy document their projects and make circuit boards available for sale to their listeners. They have interesting guests and go in deep. Even if you're a seasoned ham radio builder or just getting started, be sure to join George and Jeremy for the Ham Radio Workbench podcast. Use the link on this week's show notes page by clicking on the image. And now back to our QSO today. Apparently there was a HamSci workshop last May. You made a lecture called Ion TV Using WWV Timing Reference Signals to Observe Ionospheric Variation. Do you have any comments on the potential demise of WWV and how it might impact your research and amateur radio in general?
I do. WWV is an excellent example of something I would call an asymmetric measurement or an asymmetric opportunity. I will give you one example. The GPS cluster has been revolutionary for people navigating from point A to point B. I mean, it's just transformed our lives. It's in nearly every device I can think of that needs to know where you are or where you're going. GPS is a wonderful example of an asymmetric system where almost all the money is spent by an agency, in that case the U.S., to put satellites up, to maintain their clocks, to do everything necessary to calibrate that end so that you can go get your $2 chip from some manufacturer and you can receive these signals and get navigation information. It turns out, by the way, that has ionospheric information buried in that. We actually use that as a research tool. The community's been doing that for about 20 years, actually. Getting back to WWV. WWV has the same flavor. The people at the National Institutes of Standards and Technology in the U.S., their primary goal is to maintain accurate time and frequency standards. And so long before the Internet, WWV, my colleagues tell me, was in fact the way that they would synchronize their professional instruments. For those people who know about network time protocol, if you look, which normally people use GPS receivers now to set a Stratum 1 NTP server, and then you synchronize your computer off that. If you look in the protocol, there is actually still a slot that describes how you would use a WWV receiver to distribute time, because at one point that's what people used. That is a reliable measurement. The frequency is really locked. It's very stable. And so one of the things that I did in the lecture you're talking about was try to figure out, okay, if I know that there's this very stable thing and I just have a regular, amateur grade receiver or even a software defined receiver, or maybe even one I don't even have on my desk but I can get to through the web. There are these things called web SDRs, Kiwi SDRs that are available that you can actually pull, the WWV clock signal off of. Could I figure out something scientifically about the ionosphere by listening to WWV on a long path? something that I knew had propagated from the at HF, 10 megahertz, 10 megahertz, 15 megahertz, from the station in Fort Collins, Colorado to me. Turns out that there is. I'm pretty sure that if I just look at what the difference is in the arrival of a second tick. Do you ever listen to WWV? That's one of the first signals that anyone who touches a radio listens to. You will hear a low thump, thump, and that's a 100 hertz subcarrier that happens every single second with a defined edge. All I did was take a look at those edges and measure the difference between one tick to the next. If you take that data near the WWD transmitter, they're very tightly packed. If you take them on an ionospheric path, they're actually spread, meaning that there's micro fluctuations in the path between you and the transmitter that must have been caused by the ionosphere. So for me, having WWV there is a wonderful opportunity to get a very low-cost yet distributed ionospheric monitor that would be very easy for people to participate in. All you need is an AM-capable receiver. They transmit AM, double sideband with a carrier. So I think it's important not to throw what looks like old technology out with the bathwater, and so we've made that. We have also added our voice to those people in the U.S. that are basically arguing for not turning WWD off but keeping it on. There's a similar time signal, of course, in Canada, CHU, but it's a little differently formatted. The one at WWD is a little better for this purpose. So I certainly hope that WWD continues. I did watch the budget negotiations this year rather carefully, and it appears at the last moment that WWD was taken off the table, but that certainly does not mean that it might not go back on. So we're hoping that continues, and we'll do our best to add our voice to it.
There was something in the news probably in the last month or two about potential issues with GPS, that GPS could go out. And as I had mentioned to you before we started, that even cranes on loading docks, in seaports use GPS to be able to move containers from one side of the port to the other. Do you see any issues with GPS, and what would the implications be for space science?
GPS indeed is used, just as you said, for precise navigation along inland waterways. One application of GPS that people also don't necessarily understand is that the primary goal of GPS is not to give navigation signals, it's actually to distribute time. The fact that it distributes an accurate time means that you can measure the delay along the path from your ground station to the satellite, and if you measure more than 4 of them, you can localize yourself on a sphere. And so wide global coordinated time distribution is the key factor that keeps GPS going. Now, if you have radio interference that kind of nestles up to those areas, or if you have, for example, even natural processes like scintillation, these are little embedded irregularities that happen in the ionosphere that, frankly, we don't completely understand yet. We've been working at it for a while. Those have impacts on precise GPS navigation. So, the applications community is working hard to try to understand them, but ultimately it all does come back to understanding our environment. This is understanding the weather in space, understanding natural ionospheric variability and how that might affect GPS. So I'd say there are 2 answers there. The first one is that we need to understand the natural environment better that our signals are passing through from satellite to ground. But the second thing is also to keep them interference-free. And that's, of course, a very familiar topic for anybody who is enjoying what I liked Steve Bibles, who I know you interviewed just recently. Steve used a really good phrase, which he said, when he said, the amateur allocations are sort of the national parks, and we need to make sure that the national parks remain enjoyable by everyone. There are intense commercial pressures now to encroach into the national parks, and the amateur radio community can help through things like the International Amateur Radio Union to sort of head off some of that encroachment and keep the bands open for advancement of the radio art. And I think the GPS bands are no less a a place that applies to.
Do you also use amateur radio beacons, various bands, for looking at propagation and how it may work? Are you using all kinds of of different technologies in order to determine what the bands are looking like?
Yes, we do. In fact, there's an entire sort of branch of study. It's called some people call it passive radar. If you come from the applications world, you hear it called signals of opportunity. What that is can you make a remote sensor when you don't control the transmitter? When the transmitter is doing whatever it's doing, can you somehow extract information from that? A beacon is a wonderful signal because for a good amount of its transmission, usually for long blocks, it's unmodulated. It's just a CW tone. So if you see any spectral spreading or anything else on that when you receive it somewhere else, the medium in between you and it must have caused that. Beacons are wonderful. I have a colleague up at Dartmouth who actually, a college in New Hampshire here in the U.S., who has been for several years trying to use commercial AM radio stations because what's AM? It's a constant carrier with sidebands. And watching down at 1 megahertz, so this is below 160 meters. This is getting to the new 630 meter band, kind of somewhere in the middle. Watching fluctuations in the carrier to again attempt to determine ionospheric information. So kind of trying to back out what the medium must have been doing to cause these fluctuations. HF beacons, same way. Right on up through the spectrum, and I know that the international beacon community is that what's happening really is that the professional community is beginning to wake up and say, wow, there's all of these signals out there, some of which have more interesting qualities than others, but we can use all of it. And what if we try to use most of it together rather than individually looking at a particular beacon? What if we can sort of aggregate what's going on? That's been some of the early work we've done at HamSci, and the papers that Dr. Frizzell and other people have published in peer-reviewed journals have been using this collective set to try to do that science with whatever we can find. And you can use any data you can find as long as you can understand what uncertainties it has and what you do and do not, what you are and are not able to measure. And so, yes, I would say that beacons are a great source of that, whether they're, by the way, on orbiting satellites or whether they're on the ground.
If you're using beacons, do you happen to have to know the power output or the effective radiated power from the antenna on that beacon and the kind of antenna? I mean, in order for the data to be really valuable, would you have to standardize on the transmitting setup of beacons across the world? An example I might give you is Soda Beams in the UK makes a little milliwatt WhisperLight transmitter, which is used for testing antennas. But interestingly enough, it works on WhisperNet. And so therefore, if you had a standard, say, vertical antenna on 40 meters, could a flock of those across the world, for lack of a better word, a whole bunch of them across the world, could that give you really valuable information?
Yes, it could. I'd say that we are on level 1 of using the information we have. Essentially, the initial studies that people have done through the HamSci Collective and other related efforts, the only thing one trusts is that there was a path open between point A and point B. So far, because we don't know necessarily what the calibrated power is, we don't know what the antenna pattern is, but we know that something was open between A and B. But the collective source of all of those paths and how they change, and anyone who has looked at WhisperNet's maps or PSK Reporter's maps can see this, there is information that you understand by just understanding what's open. I would say that that's level 1. Level 2, and this is the work that HamSci is now engaged in collaboration with Tapper, and I know that you have just talked to Steve Biebel not that long ago. the idea is, can we go farther? Can we get some kind of reference antenna, which, as you said, is calibrated somewhat, as you're talking about? Can we get an SDR, a software-defined radio, that is a little purpose-built for these kind of measurements? And can we put it together in an affordable enough package that we can start building the networks to go to, I would say, level 2, where one does have some calibrated things? One has calibrated power. One has a calibrated antenna pattern. One makes measurements, including, for example, beacon quality measurements on different cadences. So that's the discussion that we're engaged in right now. I think the future is quite bright for that, but it's a little early days to see exactly how that's going to settle.
I noticed from your QRZ page that you have a recent entry where you now have one of Pavel Demon's 8-band FT8 receivers using the red Pitya. Can you explain what that is and what you're learning from it?
I will. By the way, that research started by listening to your interview with Rich Zwerko, K1HTV, on this very program. So perhaps the loop has closed there.
Well, thank you. That's good to know.
Hey, the information was wonderful. And I had worked with Pavel before, kind of helping to test some early versions of his software with the Red Pitaya, but I had not understood that he had this particular decoder. So just very basically what it is, those people who, have been paying any attention at all to the digital revolution know that the popularity of the FT8 mode, that F is for Frank, and the T is for Taylor. That's Steve Frank and Joe Taylor. And the 8 happens to do with the number of frequencies that are being transmitted. This is an extremely sophisticated weak signal coding transmission that allows one to pull signals out well below the noise floor of most of the traditional modulation patterns like CW, AM, single sideband, that sort of thing. And it's been, as one knows, it's been widely adopted by a bunch of people, especially here at Solar Minimum, where, things like 10 meters and 12 meters don't open to traditional stuff that often, and where the propagation for conventional things can be a little bit dismal. So Pavel wrote essentially, this Red Pitaya is essentially a general purpose device. The word was the Swiss Army knife for engineers. It's a little board that essentially runs a form of embedded Linux, and it has 2 receiver inputs and 2 transmitter outputs. But pertinent to this conversation, one of the receiver outputs goes through an op-amp and straight into a floating point gate array, or FPGA, which is very programmable and can do things rather fast. So Pavel designed a little program which essentially divided the FPGA up into 8 identical receiver slices. Receiver slice should be familiar to anyone who's worked with a flex radio. They will develop, you can have 4 receiver slices and they can be tuned to different frequencies. So Pavel created this little image which essentially has 8 receiver slices, and you can set your choice of 8 bands. So you set the 8 receiver slices to each of 8 FT8 watering holes, 14.074 megahertz for 20 meters, 7.074 megahertz for 40 meters, and so on. And it sits there and takes data for 15 seconds and then engages its little decoder, decodes the signals it hears, records all of the information that comes out of the FT8 algorithm, and then just uploads it to PSK Reporter. And it does this over and over again. And that's its job. If you plug it into a little Ethernet port and apply power, it starts doing this. So I thought, oh, well, that's attractive. It's interesting let's just see how many things, it sees if I do that. So I went home and hooked it up to my little router on my home network and took the fan dipole in the backyard. My friend Will put that together, of course, and wasn't using it. An 80, 40, and 20 meter dipole, 3 wires. Threw that on there, and I have to say, the next morning when I woke up and I look at the statistics, I could hardly believe what I saw. I kept that running for about a day, and in a day I had over 20,000 decodes from about 125 countries.
Did you see activity in all 8 bands?
Yes, I did.
Wow.
Including the higher ones. At Solar Minimum, from a nothing with very much gain, and it's been continuing like that the whole time. And these are propagation paths to Europe, to South America, to Australia, to New Zealand. I took some of the data from Philip Gladstone's wonderful work with PSK Reporter, did a little bit of binning on it, made some maps, and every day, like clockwork, I can see Japan light up for about 2 hours when gray line propagation happens and it goes away after that. If you are a curious person and you're interested in learning how propagation works at your QTH on your antenna, I cannot recommend that thing highly enough. It's truly amazing. From a professional point of view, what I find extremely interesting is that a lot of those paths are not really reproduced by the current electron density models or the best propagation software. So by contributing that, literally just measure FT8 with a little device that you don't even touch, disconnecting, of course, if you're transmitting. If you just do that, you're generating a lot of data that it's going to take the professional community some time to even catch up to. So another really exciting thing, I think. And I kind of just stumbled into it as what any citizen scientist would do. Oh, that looks interesting. I'll just plug it in and see what happens.
And now this message from QRP Labs. Hans Summers, G0UPL, the ham behind QRP Labs, has created a wide range of radios and radio accessories to make your kit building fun and successful. Hans created the ultimate Arduino Shield kit that allows you to install this board on an Arduino board, header pins to header socket. With the addition of the SI5351 synthesizer, GPS receiver board, and a low-pass filter, you have a fully automated WhisperNet transmitter. With QRP Labs kits and accessories, there's no stopping the ham that wants to continue to add features, bands, and system capability. What a better way to build a great rig over time on a limited budget and become a master of what's under the lid. For the hands-on learner, this is the best way to become an expert. Be sure to use the links on the show notes pages to get to QRP Labs to tell Hans that you heard it here on QSO Today. QRP Labs is my favorite kit company. It should be yours too. And now back to QSO Today. Well, I hate to ask the question to a guy that's sitting on a 1,000,000-watt transmitter, but do you think that the weak signal propagation is as interesting as the high power signal stuff that you've been doing at Haystack?
Absolutely. I think that if I spend my professional life here with, as you say, a megawatt class pulsed system, which, I tell people is QRO, and then you can add 3 or 4 O's, I guess. But no, the weak signal stuff is equally as fascinating to me because it's uncovering features of even the quiet time, relatively low density ionosphere that I had not suspected at all were there. And I have some professional colleagues who also sort of scratch their heads and saying, well, empirically, I know they're there. I have yet to figure out why. RF propagation, and we get spoiled, at least superficially, by going to things like the Voice of America, the VOA CAP website. There's one of those that you can search, which will give you propagation predictions for your location. It was developed by the Voice of America originally, and that code is lovely. But it's a very heavily averaged code, and these particular weak signal paths are kind of at the forefront of what we understand or don't understand about the weather in the upper atmosphere. And so I'm very interested in, just from both an amateur and a professional point of view, in seeing what we can figure out about this. One other thing to mention about that I was really shocked by was going to the pskreporter.info website, which Philip Gladstone maintains. And if you go look at a map and, make any plot you'd like, at the bottom of that, in the lower left-hand corner, there's a little link that says statistics. And if you go to statistics, you get another page that opens up, which will show you a bunch of fascinating curves about how many stations we're on in over the last few days or week or 2 weeks. And then there's a sort of a top 10 list or a top something list of how many people had decoded things in 24 hours. But if you go down to the page at the bottom, there is the number of FT8 reports that had happened over the last 2 hours. And FT8 has 2 orders of magnitude more detections than any other mode I mean, it isn't even close. So just the number of people that are out there transmitting, making contacts, this is an absolute gold mine for people who are doing ionospheric research. So I'm really excited about it just from that point of view alone.
So it leads you to believe then that, or it leads me to believe then, that those paths that all around the world from MyQTH are there all the time, regardless of whether the sunspot cycle is at its high or at its low. But depending upon the density of the ionosphere, our ability to operate conventional modes like single sideband and CW are impaired maybe by the low sunspot cycle.
Precisely. That's the way I look at it. That's exactly the way I look at it. I also will point out that by literally downloading WSJTX and making some FT8 contacts, if you wish to go deeper, you are using weak signal communication codes that are absolutely the cutting edge. I mean, there is nothing in the professional literature that works that's much significantly better than the work that Joe Taylor and Steve Frank have put in there. These are extraordinary things. So I know that the typical ham, when they look at that initially, it doesn't have the human factor of picking up the microphone and making that contact and hearing that human voice. But if you are at all technically inclined, these are the best that it gets. And I think that what happens is that by using those codes, and as you probably know, the whole WSJTX team is still innovating. In fact, my inbox pinged this morning with the fact that they are now releasing 2.1.0, which has the FT4 mode in it, which is even faster than FT8. My point is that by participating in this, you are also doing communications weak signal research. Again, by participating and uploading your data and sharing it with the community. This is a very different time than we have been experiencing even a few years beforehand. But it's not to say that people can enjoy the conventional contacts that they've always made on CW or even or sideband or even AM. It's just that now you have so much more information about when to do it. When is going to be best from where you are? And if you're a limited time person, say you have a family and you're trying to maximize your hour or two that you have at the radio, engaging your curiosity and looking at that data and figuring out when I would actually be able to do that is going to get you a lot farther. It's just a wonderful set of tools we have.
Tapper has a project called the Tangerine Space SDR, and you have some interest in it. What is that? What is the Tangerine Space SDR?
The Tangerine SDR grew out of some discussions that we had at the last September in 2018 at the Tapper workshop, which occurred in Albuquerque. The Sunday morning discussion is usually a long-form one that takes the whole morning and goes on a deep dive into a particular topic. So members of the Hamsci Collective came along, and we gave an introduction to what we were interested in from a professional ionospheric research point of view, and then asked Tapper, since you make devices, very clever devices that then you can put into limited production, would it be possible to make an SDR, software-defined radio, that would in fact be tuned to generate a little more specific data that could be used for scientific purposes, while at the same time providing the ham who installs it with some local information, kind of similar to that FT8 monitor that I just talked about how are things doing at my QTH? How can I improve my setup? Am I having a problem hearing the west coast of the U.S. where other people can hear it, for example, at the same time? So when we had this discussion, the Tapper folks, who are excellent at making things, going through the formal design process, and then hardening a product that then they can offer in limited quantities, came up with the Tangerine SDR as a way to sort of coalesce the discussion and the design process on an SDR that would, for example, be able to make some more calibrated measurements, that would have more precise timing than was available, for example, somehow involving some kind of a GPS discipline oscillator, so that there is a accurate frequency reference. There is a way to determine accurate global time by pulling universal time off the GPS cluster. So the Tangerine SDR is sort of in that cycling process right now. There's some mailing lists. People are quite actively participating in it. I expect to have more discussions with Tapper at the upcoming September meeting. And if you go through the HamSci website at hamsci.org, there is some information in there on what people are now calling the personal space weather station. That's, again, a way for a ham to have something that both makes advanced scientific contributions and also does something that advances their own enjoyment of the hobby. And it's a balance, but we're hoping that we can get there. So that's where and I think the Tangerine SDR name came from some way to make a catchy thing that was, would stick in someone's mind, which I think it has already.
Right. It reminds me of a song. And, of course, a link to this and to everything else that we're discussing is in the show notes of the QSO Today website. To throw a monkey wrench into this, I never want to be political on the QSO Today podcast, but, when I have a guy like you as a guest, it seems to me that I can ask some questions that might be a little bit out there. Does your work in the upper atmosphere lead you to conclude that perhaps man is responsible for climate change, and is there anything that we can do about it?
So my response to that would be that the work that we do at Haystack has revealed that we need to be much more, how shall I say this, global in our understanding of the atmosphere to understand both the natural and the man-made effects. I have colleagues, for example, who study long-term trends. If you make the same kind of measurement in the upper atmosphere for 50 years, you have a fairly good baseline, and some of the signals there of longer-term trends are larger amplitude than they are in looking at a bunch of thermometers here in the ground, which would make some sense if you think about it. There's a lot of atmosphere on the ground, so if you put a given amount of energy into the atmosphere, more particles means smaller temperature changes. If you go up in the upper atmosphere, less density, larger changes, because the density times the temperature is the sort of measure of the energy in a box of atmosphere. So I have colleagues who have been looking at our trends, over the last 50 years, and they do detect, temperature changes that but we're trying to understand those because those are actually coupled to the fact that the atmosphere is not a stationary thing. We know every day when we go out there, if there's a storm front coming, there's a lot of wind blowing in our face. It turns out there are motions all over the place in the atmosphere, and some of the motions are not only blowing horizontally but also vertically. And so they're actually coupling waves that come from the lower atmosphere into the upper atmosphere. So there's actually a form of weather in the upper atmosphere that comes from the ground, not only from outside in the sun, and you hear about things like solar flares and coronal mass ejections, which cause geomagnetic storms, which don't really thrill people trying to make HF contacts. But my point here is that we are still trying to wrap our arms around the fact that we need to understand the whole atmosphere, kind of from sun to mud is the phrase I heard. And so until we understand that, it's a little difficult to see if there's anything specific that we can do, partly because our coupled models are still trying to catch up to our observations in terms of understanding the consequences of, doubling CO2 and that sort of thing. So I would say that the research has basically told me that life is a complicated thing, and the upper atmospheres and the lower atmosphere is a very complicated thing. So it's a little hard to answer that question. I will tell you, though, that I am fully convinced that there are definitely anthropomorphic changes that humans are making in this particular system. And, that's a large experiment that it might not be wise to continue because we don't necessarily know the outcome, and some of the outcomes are rather dire. So there's a connected point here. We were talking about the ability for amateurs and professionals to meet in the middle. And one of the things that we scientists spend our entire days trying to convince ourselves of is that we didn't do something wrong. Okay, the rejecting the null hypothesis is the first thing you ever do in any scientific measurement, which is essentially just to reject the likely probability that the two things that you're trying to think they have a connection to are not connected. And that takes a lot of work, and that's part of the reason why we have peer-reviewed papers and that sort of thing. The dialogue about how to – we think we can, in fact, advance science, but what we have to do is think about how to not do the what people call post hoc analysis, which is essentially to say, my dog barked and then there was an earthquake. Therefore, every time there's therefore my dog barking is a precursor to the earthquake. Well, we haven't quite figured out the number of times your dog barked and there was no earthquake. There's a wonderful website which I recommend everybody try to find through Google. It's called Spurious Correlations. It's a person that tries to illustrate the point that correlation is not causation. Just because two things are perfectly correlated doesn't mean one causes the other. And this fellow who does this website has come up with some spectacular ones. I'll just give you the title of one of them I have on my screen now, which is The Divorce Rate in Maine Perfectly Correlates with the Per Capita Consumption of Margarine. These are two things that have absolutely no relation to one another, yet they are, in fact, perfectly correlated over more than a decade. If you just take that correlation and say that, well, if I eat less margarine, I won't get divorced, well, okay, that's pretty silly. But it's very easy in science to do the same thing. So that's one of the things that we're trying to do in the amateur-professional connection is try to understand how to not fall into those traps, and also, by inference, how to train more people who are coming to this with curiosity and for fun about how to do the more rigorous thing, with the caveat that, hey, we're professionals and we know how to do this. We know how to get stuff in journals, so let's work together.
Well, it reminds me of, in the 70s when there was a physicist at UC Irvine who was talking about the problem of fluorocarbons in the atmosphere and causing the hole in the ozone layer. And so the way that industry and society adapted was to take the fluorocarbons out of spray cans, for example. I don't know what that meant that the ozone layer or the hole in the ozone layer was now healed because we're no longer spraying underarm deodorant. We're using a solid or stick.
I was going to say, well, what that means is that we stopped putting a source into the system. And so what we now do is we now try to say, well, where was that source going? What were the circulation patterns? Mm-hmm. Where is the hole still there, but it's migrated somewhere else? Or how long do we predict that the system will take to recover to a nominal level? But it's prediction. There are some predictions that are, very solid, and there are some predictions that you just don't have enough data yet. I think it's very, very solid that anthropomorphic change is happening. Okay, I don't think there's really no question through many, 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 many different kinds of things. The ability to predict in every detail what will happen is probably more difficult, but I think there are certain basic conclusions that we can come to, and that, the weather is going to get more variable. There's kind of no two ways around that. Most of the models show you that. So dealing with the extremes of variability is going to become an increasing societal problem. And I think the last 2 years or 3 years, just watching the normal weather patterns, you're beginning to see that.
For a lot of different reasons, we tend to, industry, science, people, we tend to adapt and adjust in order to prevent something catastrophic. We heard the message about fluorocarbons, and we were able to practically eliminate them from air conditioning systems and spray cans. So I think we have that ability also. When it comes to reducing CO2. Does climate change lead to changes in radio propagation, do you think?
So one of the complications of climate change is that the atmosphere actually reacts with different profiles, different temperature changes at different levels. So we talk about global warming. That's in the very lower atmosphere, and as you go up in altitude, there's a place where global cooling occurs. Near the mesosphere, the temperatures actually start getting colder. And then above that, the temperatures get hotter. Then they get colder. There are actually different levels. That's because the amount of wave activity in the atmosphere transferring energy from one place to another one is very different at different altitudes. So another reason why the response to the system is very complex. Now, if we're talking about the part of the atmosphere that does the HF propagation that we use as amateurs, that's, starting at about 90 to 100 kilometers altitude, where the electron density is sufficiently dense to have an effect on propagation, and going up from there, it certainly does have an effect. The mean altitude of, say, the electron density peak, which is the place that does, some of the, for example, especially at nighttime, transcontinental propagation there's no E region anymore. The chemistry has sort of made it go away about an hour after the sun turns off. You're left with the F region. That layer and that altitude is going to determine sort of the refraction points and therefore the distance between A and B. That layer is changing because the temperature in the upper atmosphere is in fact changing. So over a long term, yes, it will have some effect. Projecting that into actual propagation paths is a work in progress. But there's definitely going to be some kind of effect in there, which if you're a interested science person, you can study. If you're an interested person who wants to just get on with it and use the link, you need to abstract that science and say, well, what does it mean for me?
Do you have an opinion on what the greatest challenge is facing amateur radio now?
I would say that right now, that wonderful pace of technology that I mentioned before that's generating really innovative software, really innovative hardware, can get ahead of the ham that hasn't necessarily been keeping up with this furious pace of innovation for any number of reasons. Maybe, again, they're in the middle of their career, they have a family, or they just have missed some of it. I think re-education, even of the folks who have been there for a while, to understand some of these possibilities, to understand that we can raise all boats by essentially trying to get everybody in a more level playing field, I think is a challenge. That, I believe, would also address some of the inevitable, that's not the way we used to do it sort of responses that you get from people who have been around for a while and are feeling comfortable using a particular mode. This is long before my time, but my understanding is, for example, that single sideband at one point was looked at as, well, we just use AM, why do we need this single sideband thing? So any new technology, such as digital modes, is inevitably going to run into this, but I think that it just means that we need to do more education. We need to talk on more programs like this one. We need to get people to understand that it's an and, not an or.
What excites you the most about what's happening in amateur radio now?
That's right. In addition to all the stuff I've just mentioned, weak signal propagation, the science those data contain, amateur scientist partnerships, the technology available at pennies on the dollar. The other thing that I think is really exciting is the number of learning resources out there on YouTube, for example. I mean, I think you've had Alan Wolk, W2AEW, on
yes.
here. People like Paul Carlson, who has Mr. Carlson's Lab, which has an enormous following. There's a lot of seriously good material out there that's wonderful, and even for somebody like me who's going back to refresh his memory after a little while on certain subjects, has been tremendous. That's really exciting to me.
It's an amazing time to be a ham radio operator, I think. As a new ham, do you have advice that you'd give to new hams?
Sure. One of the things that I find so extraordinary and fun, frankly, about ham radio is it's populated with a bunch of people who are curious, okay? And they're also extremely keen observers of what's going on, because how can you participate in the hobby if you don't pay attention to what works and what doesn't? So feeding your curiosity and engaging in lifelong learning, that is a key phrase, is probably the most important thing I could encourage even a new ham to do. It may look intimidating at the beginning. There's all these subjects. How could I possibly, I can't absorb all this. You don't have to absorb all of it. Pick one of them and socialize. Go find a club. Go find an Elmer. Go find somebody even online who can drop them an email, write them a tweet, ask them a question. And when you're doing that, when you've gotten the other advice I give is when you've gotten yourself up a little bit so you understand some of what you're doing, turn around and teach it to somebody else. The best way for you to understand what you're doing is to teach it to somebody else. Do that at the local level. Show up in your club and say, hey, I've been playing with this FD8 monitor thing. Let's just talk about it. I'll show you how it works. Does anybody recognize anything in here? And contribute your observations to things like HamSci, to things like other organized efforts, and, make it a collective pursuit. I think that's the most important thing, is to not sort of be isolated about it, but to plug yourself into the community, and it will give you back much, much more than you ever thought at the beginning.
Well, Phil, I'm so grateful and excited that you agreed to be my guest on the QSO Today podcast. I want to mention to the listeners that in terms of finding a mentor, a ham radio mentor, you've just listened to the 259th ham radio mentor on the QSO Today podcast, and almost all of with the exception of those who are now silent key, almost all of the previous guests of the QSO Today podcast are available and anxious to hear from you if you have questions about anything that you can learn in ham radio. So, Phil, I want to thank you so much for coming on the QSO Today podcast. And with that, I want to wish you 73.
It's been my real honor. I've enjoyed your podcast very much, and it's been a lot of fun talking about things that excite me. So it's been a fabulous QSO. Thank you again very much, Eric, and 73 to you and all the listeners.
Thanks so much, Phil. 73. That concludes this episode of QSO Today. I hope that you enjoyed this QSO with Phil. Please be sure to check out the show notes that include links and information about the topics that we discussed. Go to www.qsotoday.com and put in W1PJE in the search box at the top of the page. My thanks to both ICOM America and QRP Labs for their support of the QSO Today podcast. Please show your support of these fine sponsors by clicking on their links in the show notes pages, or when you make your purchases, that you say that you heard it here on QSO Today. You may notice that some of the episodes are transcribed into written text. If you'd like to sponsor this or any of the other episodes into written text, please contact me. Support the QSO Today podcast by first joining the QSO Today email list by pressing the subscribe buttons on the show notes pages. I will not spam you or share your email address with anyone. Become a listener sponsor monthly or annually by clicking on the sponsor buttons on the show notes page. I am grateful for any way that you show appreciation and support. It makes a big difference. QSO Today is now available on iHeartRadio, Spotify, Libsyn, and TuneIn, as well as the iTunes Store. If you own an Amazon Echo, you can say, Alicia, play the QSO Today podcast from TuneIn. I still use Stitcher to listen to podcasts on my smartphone. The links to all of these services are on the show notes pages on the right side. Until next time, this is Eric 4Z1UG 73. The QSO Today podcast is a product of KEG Media Inc., who is solely responsible for its content.